Okay, thank you. Thank you very much, Michael, for the organization of this conference and for inviting me and introducing me. My name is Woo Hwi Yang, and I'm from China University, South Korea. I would like to introduce our research topic. This is a modified formula of pure maximal glycolytic rate as PvLa.max. Second. The slides don't move.
Did you share the application, or did you share your screen?
Okay.
No, they don't seem to be moving on our end either. Maybe if you stop sharing them and then try to reshare, they sometimes that might help.
Sorry.
Sorry, no, that's absolutely fine.
I can't understand why I don't move my slide. Oh, yes. Oh.
Yeah.
Right?
Excellent.
Yeah.
Yes, I can see that.
Yeah.
Excellent.
This study, we know already this study is already published in 2023 with our colleague Sebastian Gellert and Oliver Heine. For introduction, human energy systems are simultaneously utilized during different exercises, such as phosphorylation glycolytic and oxidative systems. However, the energy consumption depends on exercise intensity and duration, which energy system is predominantly used. We or many scientific colleagues worldwide focus on glycolytic metabolism, which supports metabolic powerful performance, and we know already that lactate production as glycolytic pathways occurs independently of oxygen availability, such as under anoxic, hypoxic, and normoxic conditions, and lactate is no more fatigue agent during different exercises. For example, track cyclists need anaerobic performance during a 1,500-meter carrying race over approximately 90 to 120 seconds. Specifically, an important factor that determines the winner of such races is particularly the final all-out sprint. They need to be absolutely necessary a high aerobic performance, but high anaerobic performance power is also required. The phosphorylation system, as well as ATP-PCR, ensures the highest metabolic power or energy flux rate, which is reflected by the rate of energy transfer per unit of time. Although the energy flux rate is very high, the general capacity is low because of limited substrate stores that last for only a few muscle contractions. Moreover, the glycolytic system can resynthesize adenosine triphosphate through the non-aerobic degradation of carbohydrates and supports the metabolic energy requirements during intense exercise. This system, when compared to the phosphorylation system, is characterized by an intermediate energy flux rate and metabolic power because of the higher number of reactions and greater overall capacity from a larger amount of stored carbohydrates. In this regard, Alois Mader 1984 proposed a maximal rate of lactate accumulation or maximal glycolytic rate as PvLa.max to be used while determining the maximum glycolysis and power. This PvLa.max variable indicates the ability to perform powerfully like sprinting, and high values of PvLa.max in well-trained or typical sprinters show more than 1 millimole per liter per second. This variable also indicates that the distribution of muscle fiber types might be considered when interpreting high or low PvLa.max values in individual athletes with higher muscle mass and more glycolytic type 2A and X fibers, who show generally higher lactate production during exercises. The formula of PvLa.max is considered the delta lactate level between the maximal lactate and the resting lactate levels divided by the delta time between the total exercise and dominant phosphatin system contributed times. Furthermore, we call this TPCR because T-alert actually means the absence of the lactic system. During the initial time frame of the sprint test, it was assumed that no lactate accumulation fictitiously takes place. However, this is not true because the lactate formation occurs every time, although the lactate level during this initial time may be very low. There is an additional problem of TPCR definition in several previous studies. The TPCR minus 3.5% without providing an in-depth explanation on why the decreased 3.5% time point of the maximal power output was determined as T-alert. However, this definition originated from the precision of power measurement on early SRM bicycle ergometer, which was investigated by Sebastian Weber's diploma thesis 2003. Here on the right side, we see the peak power outputs of an early version of the SRM bicycle ergometer, which showed the differences from several measurements. Furthermore, pure PvLa.max determination cannot be precisely calculated when considering an approximate oxidative contribution of 10% during short sprints. I mean here without a calculation of the oxidative contribution. However, three metabolic contributions couldn't be separately analyzed at the time, and the oxidative contribution during the short sprint test was not calculated for PvLa.max. In light of this, we thought the PCR-La-O2 method, which is yet well-established methodology involving all three energy contributions during different exercises when calculating exercise-induced energy turnover. This method can easily be incorporated into the PvLa.max formula as the time span of relative oxidative contribution. The knowledge of energetic contributions in different sports is very important because of a better understanding of the metabolic responses in order to optimize training methods for athletes and coaches. Therefore, we compared three diverse PvLa.max calculations based on the differences in determining the phosphatin contributed time and incorporation of the oxidative energy system. Additionally, we analyzed the relationships among different PvLa.max calculations and performance-related variables, such as peak power and mean power outputs and glycolytic energy contribution. For test procedure, this was relatively easy. 30 male national level track cyclists participated in our study. You can see here characteristics of the participants, such as anthropometric data. Before the test, an initial warm-up was performed for 10 minutes at 2 watts per kilogram. and then a further passive rest for 5 minutes followed. The 15-second sprint test was conducted in the isokinetic mode set to a cadence 120 RPM. The participant performed the test in the sitting position on the bicycle ergometer and VO2 data at 5-minute rest and during the 15-second test, as well as up to 6 minutes after the test was measured. And furthermore, capillary blood was collected from Europe before and in minutes interval like first to 10th after the sprint test. For the calculation of metabolic contributions, the oxidative metabolism was calculated by subtracting VO2 rest from VO2 during the 15-second test by the trapezoidal method, in which the area under the O2 curve was divided into sections, and the sum of the trapezoid was utilized to calculate the integral. For the analysis of the glycolytic metabolism, theta lactate between rest and peak values, O2 lactate equivalent and calorie quotient were utilized. Post-fasting contribution was calculated considering VO2 and the fast component of excess post-exercise after the 15-second sprint test using the mono exponential model. Actually, the off VO2 kinetics after the 15-second sprint was fitted by mono and bi-exponential models. However, the slow component of the bi-exponential model was negligible. So we used a mono exponential model. First of all, pure PvLa.max was calculated as delta lactate divided by the difference between total sprint time and TPCR peak plus relative oxidative contribution in percentages, which was converted to time in seconds related to the total sprint time. TPCR peak was determined at the time up to peak power outputs because the accuracy of the latest SRM bicycle ergometer is reported to be from 0.5 to 1% according to the manufacturer and previous studies. The second PvLa.max was calculated with TPCR peak for the denominator, but without an oxidative contributed time span. The third PvLa.max was calculated using the Weber's method as minus 3.5% for the denominator. So from now on, to understand, I call these calculations just the PvLa.max, PvLa.max peak, and PvLa.max 3.5. Our results showed that predominant phosphatin and glycolytic energy contributions were observed. The three energy systems were significantly differentiated from each other, and the relative oxidative contribution during a 15-second sprint test was 3%. As I already explained, this percentage was utilized for PvLa.max, which indicated significant differences compared to PvLa.max 3.5 and PvLa.max peak values. We found a very strong correlation between PvLa.max and PvLa.max peak, and a high positive correlation between PvLa.max and PvLa.max 3.5. Accordingly, PvLa.max and PvLa.max peak showed lower bias and a smaller 95% limit of agreement compared to PvLa.max and PvLa.max 3.5. Furthermore, low positive correlations were observed between mean watt and all PvLa.max calculations, and moderate to high correlations between absolute glycolytic contribution and all PvLa.max calculations. So table 1 shows performance-related variables, different values of 3 PvLa.max calculations, and the converted time span of the oxidative contribution during the sprint test, which was 0.49 seconds. Moreover, peak and mean power outputs were averaged at 1,496 and 1,260 watts, respectively. For discussion, the level of PvLa.max 3.5 showed higher values than PvLa.max peak and PvLa.max because the TPCR minus 3.5 value was 3.2 seconds. So the denominator of the formula was smaller than the others. Moreover, Heck et al. Suggested that aerobic power and contribution are of minor significance, but our results indicate the significant differences in the PvLa.max calculations with and without oxidative contribution. Therefore, oxidative metabolism should be considered when aiming to analyze a pure PvLa.max. According to relationships, PvLa.max was very strongly correlated with PvLa.max peak, and this correlation was higher than that of PvLa.max with PvLa.max 3.5. Furthermore, PvLa.max and PvLa.max peak were associated with mean watt and absolute glycolytic contribution, which were higher than PvLa.max 3.5. So these results indicate that PvLa.max and PvLa.max peak are better calculating methods for glycolytic capacity or power. To determine the anaerobic performance, the 30-second wing gait anaerobic test is frequently used in sports science. However, this time frame will increase the oxidative contribution to the total energy demand and may also lead to an inhibition of phosphofructokinase activity because of accumulated hydrogen ions from increased adenosine triphosphate hydrolysis and reduced pH levels. Also, previous studies showed that the oxidative contribution can be increased up to 20 or 25% during the 30-second wing gait anaerobic test. This increased oxidative contribution can reduce lactate accumulation and increase lactate elimination, which results in a reduced maximal lactate accumulation. So the PvLa.max determination combining the 15-second sprint cycling test with the PvLa.max formula using the energy system contributions is more suitable to limit the activation of oxidative metabolism as much as possible in decreasing intracellular lactate oxidation. We successfully identified the differences of 3 possible PvLa.max calculations during the 15-second sprint cycling test. However, we have some limitations of the study. For example, although the TPCR peak determination is physiologically acceptable using the peak power output in sports science, the direct measurement considering a biomarker is very difficult or impossible. So actual direct measurements for TPCR and exact metabolic contributions have to be determined, for example, isotopic thresholds or fluorescent protein sensors in future studies. Regarding the possible gender differences in metabolic contributions, we also calculated the metabolic contributions during increasing exercise intensities like a step test in our previous study. We found different levels of absolute and relative phosphatin and glycolytic contributions between male and female adults that were attributed to the differences in skeletal muscle mass and all fiber types. So there may be a need for further or future research into gender differences in the PvLa.max calculation. Furthermore, there are currently no clear data available about which specific individual training sessions help to improve PvLa.max. A recent study by Schunemann et al. 2023 suggested that sprint training, high-intensity intermittent training such as Tabata training, resistance training, and hypoxia training may increase glycolytic capacity and anaerobic performance. it means increased activation of glycolytic enzymes. However, we need direct interventional approaches related to improving maximal glycolytic rate. For conclusions and recommendations, the calculation of PvLa.max using the analysis of energetic contributions should be considered in scientific research to precisely analyze the maximum rate of lactate accumulation and anaerobic capacity or power. In practical diagnostics, the calculation of PvLa.max peak may be useful without a complicated analysis of energetic contributions, or if it is not possible to be available for gas analyzer equipment eventually. Otherwise, we only recommend the PvLa.max 3.5 calculation if the early version of the SRM bicycle ergometer or other bicycle ergometer is available to perform the sprint test. So this was relatively a recent study outcomes, and thank you for your listening and your attention. Thank you.
Excellent. Thank you very much for that presentation. Some really, really insightful things mentioned throughout that. I think everybody's going to been using some of that going forward. I think it was really, really interesting. We do have a couple of questions in chat. I'd like to pitch one to you first. So I know a lot of the research is applied with elite populations and sporting populations, but how do you think the PvLa.max can actually be applied to, say, like non-communicable diseases and those disease populations? So I think that's quite an area that can see quite a lot of crossover with the introduction of this PvLa.max.
You mean the general population or disease population?
Yeah, disease populations like diabetes or cardiovascular disease, for example.
This is very difficult to say because they don't need this performance, actually. Yeah, so I think, in my opinion, they don't need to measure PvLa.max to determine, I don't know, for a diabetic or other non-communicable disease. So this is really, I think, the measurement for elite athletes, because as I say already, this is not really for disease population, because they don't need to show this performance. Yeah.
Okay, interesting. So something that Jamie and I have spoke about previously as well is so when you're assessing the oxygen contribution during the sprint, then what's the specific component that you're looking for? Is it just start to end of the sprint, or are you taking in some of the epoch part of the sprint as well to assess this oxidative component?
I think there are many factors, but for example, the starting before the starting the test, we have to measure resting VO2 data at least 3 minutes, and after 15 seconds or 10 seconds, we have to really measure over 6 minutes, because VO2 data is decreased after exercise, and this can reduce to a resting level. Then you can calculate this epoch and fast component and slow component using a mono or bi-exponential models. And otherwise, you don't really exactly measure the fast and slow component. So I think these are the important factors.
Excellent. Thank you very much.